7.5. A lot of this stuff will probably be new to you all, and that's okay. It's a lot of adding and subtracting and multiplying. No algebra. All right. What are these things? These are matrices. Okay? It's an array of numbers. They're in a box. Kind of looks like gobbledygook, right? These are very, very important, though. So if you take physics, you can turn arrays into matrices. You can turn equations. Did I skip a slide? No. All right. So this is the first thing you do need to know. It's m by n, where m is the rows and n is the columns. Okay? That's the dimensions of the matrix. Did I hit record? I did. There's some lovely photos on my phone from class one day. All right. All right. So let's find the dimensions of each of the matrix. Man, I'd like to make a lot of jokes about the movie, but I realized it came out in 1997, which is legitimately almost 30 years ago. All right. How many rows does this beast have? 3. How many columns? 2. That's a 3 by 2 matrix. It's almost like slope, right? Rise over run. Never noticed that before. So this one has 2 rows and 3 columns. This is actually going to be an important step when we go to plug in our calculator. Before we plug in the numbers, we need to know the dimensions of it. This one is a 3 by 3. And this one's a 1 by 3. That's the only thing on the test. Would you guys be pretty content? Good. All right. I don't care about it. This is just some definition stuff. It's not going to come up a lot. It's a square matrix if the columns equal the rows. That makes sense. And it is called a zero matrix if all the numbers inside of it are 0. That's not going to really come up in here. This isn't going to come up a whole lot. I'm going to say it sometimes, but have you guys ever played Battleship? And you give like a letter and a number, right? Like a longitude, latitude. That's what we're doing here. It's just the first number is what row are you in? The second number is what column are you on? So if I ask you for the A22, like on a homework, I'd say, hey, what's in the matrix box A22? You would tell me what's in the second row, second column. First row, second column. So the first number tells you the row, second column. Okay? Just like the numbers. It's the same order as the numbers for the dimensions of it. Okay? All right. All right, let's do this stuff. How do you add and subtract matrices? Good question. If you're adding matrix, you just add the numbers that are in the corresponding row and column together. Okay? 5 plus 2 is 7. 7 plus 0 is 7. You guys see that pattern? I like this one because it actually makes sense. It's straightforward. 2 plus -8 is -6. Okay? You guys want me to go talk about that more, or do you think you're okay? Let's do an example of it. Of matrices? Oh, I'll show you. It's going to make life a lot easier for algebra, actually. You're going to wish you knew how to use matrices through all your algebra classes you ever took, because it actually simplifies a lot of things. I don't know, because they wanted to make sure you could do a longhand. Now, this is an important thing to know. This is a common mistake. this is my first row, first column, first row, first column, right? First row, second column, first row, second column. Uh-oh, do I have a number to go with this over here? Because I do not have a number that goes with it, this is not possible to do. You cannot combine matrices that aren't the same dimensions because you don't know what to add to each other, okay? Yeah. All right, we are almost halfway through this one. I'll show you guys the new thing in a second. So scalar multiplication, if I multiply a matrix by a number, what do I do with that for? Think about like the distributive property, right? Everyone gets multiplied by 4. Every single piece gets multiplied by 4. If I divide, every single piece gets divided. Order of operations come into play, so if I'm multiplying and adding, I'll show you guys some examples of that. All right. Questions on this one? This stuff's pretty intuitive though, right? If you're multiplying, you multiply, add, you add, subtract, you subtract. Well, scalar multiplication. Okay, scalar multiplication. So let's do some examples of it. All right. Add these two matrices together. First off, can I do it? Are their dimensions the same? Yeah. So I'm just going to go through and do 4 plus 1 is 5. 9 plus negative 8 is 1. Right? 12 plus negative 3 is 9. 3 plus 14 is 17. Negative 8, 10. Sound good? There is a test question with this. Do you guys feel like would you guys be excited to see this question? Don't overthink this one. So what am I going to do with the subtraction? Be careful. I do see a lot of people make mistakes on this one because you forget that there's a negative, and that negative means I'm subtracting each, right? So that would actually be adding that. So that would be 8.1, right? 3.3 minus a negative, so you'd add them. So that'd be what? I don't know, 7. Negative 10.2 and 1.3. Yar? Okay. Okay. All right, go ahead. Try this one. Try that one. Try this one. You guys, okay. The crowd's saying they're going to fall for my tricks. This is a 2 by 2, right? This is a 2 by 3. Can I add these two together? Absolutely not. Does not exist. Like the Lions offense last night. All right. That marker's cooked.
Watch Pirates.
Get out of here. Not watching Raiders. All right. Can we do this one, though? What's that 6 go to? All of them. All of them. Yarnar. Yar. All right. Any questions on this? Are you guys feeling okay? Or is it Monday? All right. Now, this one I would like you to try. Give this one a shot. So pause the video, try it. People at home, try it. There's not a trick to this one. I will say do order of operations. Thumbs up, thumbs down. How you guys doing? So I told us that you could have distributed a -2 through or a 2 and then subtracted it. Either way, you'll get the same answer. Okay? So far, I'd say all this is pretty review because it's just how math has worked. The next thing we're going to do is new, though. Okay, so put on your focus goggles. This next thing's going to be new. It's not overly difficult. It's just new. So what we were doing before is scalar multiplication. We're making matrices are a lot of times used for vectors, which are actually a physical thing, right? They're an arrow, they're a force, and sometimes we need to make the force larger or smaller, and we use scalar multiplication to do that. And it's just lengthening the magnitude of your vector, which if you take pre-calc, you learn more about vectors, which is actually a lot of matrix stuff, which isn't bad. But what do I do if I have two matrices and I want to multiply them together? Because there's not just one number, right? There's a lot of numbers in a matrix. What can I do that? I can. I can multiply two matrices. Okay? There's going to be a way to do that. What we're going to do is I don't know, right? It's going to be like piece by piece. I don't know if you guys can see this well. So if you want to do this like on your own at the side or something, you go row times column, right? So negative 4 times 3 plus 6 times negative 1. 4 times 3, 6 times 1. And you add them together. And that'll give you row 1, column 1. Because it's row 1, column 1. So it gives you row 1, column 1 of this piece. Okay? I'll show you. This is going to look, trust me, we're going to do a bunch of examples of this. It's the same thing every time. All right? So how do you think, so again, row 1, column 1 by doing row 1 times column 1. How am I going to find row 1, column 2, do you think? How am I going to find this box right here? I'm going to do row 1 times column 2, right? So I'm going to do negative 4 times 3 plus 6. Wait, why am I looking? I'm looking at the blue. I would do row 1 times column 1. So I do negative 4 times 1 plus 6 times 5 will give me that second box. That's what, 30 minus 4, 26. Okay, if you go through your packet, a bunch of the slides now are showing you the row times column. So if you want to see it that way, that's fine. I'm just going to do it right now so you guys have like a written version of it. So now how am I going to find this row 2, column 1? Second row, first column. I'm going to use my row 2, right, times my column 1. Okay? Again, I'm not expecting you guys to get this first time. That's okay. Right? Row 2, column 1. So what's that? 36 minus 13. My brain's not firing in all cylinders yet. 23. Right? And, ooh, a pink one. So how am I going to find my row 2, column 2? I'm going to take my row 2 times my column 2. All right? So 12 times 1 plus 13 times 5. That's 65, 77. Yep. All right. Biggest thing I want you to remember is the first one, you're using rows. Second one, you're using columns. How do you write a matrix? Is rows by columns, right? Rows are always first. So I'm just using rows on this one, just using columns on this one. Okay. Again, do I expect you to get that right this second? No. Let's do another one. I'm going to have you guys try one too. Yeah, we'll do one more together. I'll have you guys try one. row times column, row times column, row times column, and that's what you get. All right, go to example 5. Example 5. This is the only thing that we're going to have to be able to do without a calculator. I want you to be able to do this. All right. All right, let's do this beast. So, on my first matrix, am I using the rows or the columns? What comes first? Rows. I'm going to use rows. Rows before rows. All right. All right, so I'm going to do row 1 times column 1, right? What space will that give me on this? Row 1, column 1, right? So I'm going to do 3 times 8 plus 5 times negative 4. I'll simplify it the next step. I'm showing you the work. Okay? Row 1, column 1 gives me row 1, column 1. Okay. I remember doing this back in the day. How am I going to find this row 1, column 2 then? I'm going to take my row 1 times column 2. Right? 3 times 4 plus 5 times negative 6. We'll simplify it next. I just want to show you, using colors and stuff, where am I getting this from? Okay? Row, column, row, column. So, once I'm done with row 1 here, I'm done with row 1 over here, right? Means I've done everything I can do with it. Run out of colors. So if I do row 2, I'm going to start with row 2. Row 2, column 1. Row 2, column 1 is going to give me row 2, column 1, right? 1 times 8 plus negative 2 times negative 4. I'm going to show you a pattern that exists with this too that's kind of neato. And lastly, row 2, column 2 will give me row 2, column 2. 1 times 4 plus negative 2 times negative 6. Here's a pattern. If you're a pattern person, what will happen every time you do this to know you did it right? 3 and 5, 3 and 5. All those first numbers in the first row should be the same, right? If it's a 10 by 10 matrix, this first row would all be 3 and 5s all the way across. 1 and negative 2, 1 and negative 2, right? So this whole second row, the first numbers will be the same as that second row. The columns are going to match up too, right? 8 and negative 4, 8 and negative 4, 8 and negative 4, 8. It would be 8 and negative 4 for every single one down that column. 4 and negative 6, 4 and negative 6, 4 and it would be the same all the way down. So what I'm saying is, you know you did this right is when you look across, you see a pattern. You look down, you see a pattern. Look across, see a pattern. Look down, you see a pattern. Okay? This is one of those things that's going to, every time you do it for a while, you're going to have to think about it. But I swear to you, it's one of those things that if you have a bunch of practice on it, it is very straightforward, actually. If you want to know what this looks like nice and simplified, it would be 4, 18. This marker's. Today's not a good day to be a marker. There it is. All right. So, I'm going to do the same thing. I want you guys to try. Go ahead and pause the video if you have it. Try the second one. Try the second one, using the first one as a template. So just a reminder, if you're following along at home, quick check. 8 and 4, right? -4, -6, -4, -6. So my rows are the same. 3 and 1, 3 and 1, 5, -2, 5, -2. I used to, like I said, in college, when we had to do big matrices, I would legitimately just write my 8 and 4s all the way across. I would do my columns all the way down. You know what I mean? Just because then I would be in the mindset where I'm not thinking each one, just doing all the columns down, all the rows across. Became very robotic. So what do you get for an answer on this piece? That's not even the right packet. Mr. Twillier, you're losing your mind. That's okay. I got 28, 32, -18, and -8. Okay? Okay. We'll do. Oh, we're doing good. Uh-oh. Let's talk about some properties. This does come up on the homework. It'll ask you what properties are true. One thing that's really... Oh. Yeah, that's what I was supposed to show you before. Go back a slide for a second. What do you notice about these two matrices and these two matrices? They're the same, right? We just flipped order. Did we get the same answer if when we changed the order of how we multiply them? Yeah, we did. So for matrix multiplication, does order matter? Extremely. It is not, A times B is not the same as B times A for matrices. And we just proved it. You guys just did a proof. So adding is commutative. Adding is commutative. Multiplication is not. Multiplication is not. Okay? Because it changes which one gives you the rows and which gives you the columns. Okay, so the order is going to matter for multiplying two matrices. Good. Good. All right. All right. All right. I'm gonna do this one. Uh-oh, Mr. Twilliger. I confused. This is a 2 by 2, and this is a 2 by 3 matrix. And we can't do operations on each other. Let's try it and see what happens. So let's try this and see what happens. So I'm taking my row times each column, right? Is there any reason I cannot take that row and times it by each column? What do you guys think? I'm going to do my -2 times 2 plus -1 times -7, right? -2 times 4 plus -1 times -2, -2 times 3 plus -1 times 0. Can I do that? All right. Let's check. -2, -1, -2, -1, -2, -1. It works, doesn't it? So do our matrix dimensions have to be the same to multiply matrices? No, they don't. Because I'm going to take my 1 and 5. I'm going to do 1 times 2 plus 5 times -7. Hey, do you guys want to know a shortcut to doing this quicker? So what I do, as long as I did those right, I don't have to look back at the matrix, right? Like, I'm going to do my 1, 4 plus 5 times -2, right? I'm getting these numbers from up there. You don't have to do it that way. It's just I had to how did I do it so quick? Once you have these two done, or this row done, you should be able to just plug and chug. 5 times 0. All right? Gentlemen. All right. So can I do a 2 by 2 times a 2 by 3 matrix? Yep. All right. What's dimensions of this matrix? 2 by 3 and 2 by 2, right? I told you dimensions do matter, like being able to find what dimension you're in. Let's try this one. So I'm going to take my first row, right, and times it by this column. If I go to do that, what's going to happen? Is there enough numbers here to do it? So this one does not exist. Here's my critical thinking question for you guys. Why does the top one exist but not the bottom one? What's the difference between those two? Why would the top one exist but not the bottom? They're both the same matrices. Here's the magic. These middle numbers have to match. If they don't match, you cannot multiply them. Right? If the two numbers next to each other do not match. And that's what this says. This basically says that you cannot multiply two matrices unless these numbers match. I actually really like this dimension behavior rule. Perfect. Can we multiply these? What's going to be the size of the resulting matrix? Massive? I wouldn't say. It's a 3 by 3 times a 3 by 3. So the resulting one will be a 3 by 3. It's the front and the back of the... Which makes sense. Are you guys okay with... I'm going to show you how to do the first one. And then it's going to be the same. So like, I take my row times my column. Does it work? 2 times 8 plus negative 3 times 0 plus 1 times 7. Right? Can I do that? Yeah. If you would like to play along at home, you can try this one out, and I'll give you the answer. This is a good thing to practice. So if you're coming up to test day and you want an extra practice problem, this would be a good one to look at. Sound good? Perfect. Yipers. All right, one more. Well, yeah. We're actually doing well. All right. Here's what this is going to show you. Is it okay if I'm going to take a little shortcut on this? If I add these first and then multiply by this matrix, I get the same thing than if I were to multiply first and then add. Okay? This is a proof. You guys, what property is it that allows me to do this? Distributive property. So does distributive property work for matrices? It does, actually, it does. So this will come up, start of this one, this does come up on your homework. It will ask you a question for which properties hold true. What's the only property that doesn't hold true from matrix multiplication that holds true for all other numbers? There's only one that doesn't hold true. The order. Yep, commutative. This is the only property that does not hold. Every other property from multiplication that you've learned in your life does. Okay? And?
That's it.